We now combine several of the concepts we discussed in earlier videos.
We will construct a C program to convert the input from decimal representation to binary.
The program will delegate some of the work to subroutines, some of which will be recursive.
We could extract the binary representation from the word where we read the integer.
However, we want to illustrate allocating an array where each entry is the char for a binary digit.
Thus, we will have a version with indexing and another with pointers.
Since different inputs to the program require different array lengths, or storage, the code shall allocate the space at runtime, that is, dynamically.
How many characters do we need for the binary representation of a positive integer number?
We recall our earlier video and define the algorithm's pseudocode starting for the small base case.
The last bit is 0 if the given value is divisible by 2.
If the given value has a non-zero remainder when divided by 2, then the last bit is 1.
Moreover, given the binary of half the given value, the binary of the input value is the concatenation with the last bit.
Before we convert our pseudocode to C code, it is good practice to design how to invoke our code.
Defining tests for a subroutine, ahead of completing the subroutine's code, assists in the design of its interface.
Test-driven development is now a crucial practice in software engineering to achieve high-quality software and to maintain and add functionality to working code without regressions.
Regressions are failures in earlier code introduced when extending its functionality.
The C subroutine that computes the length in binary of a given value is succinct.
While in assembly, because we use recursion, we will need to place the return address in the stack, and also we will need a res register to save the one parameter.
The core is the if-then-else control structure, testing for the negation to jump to the else's label.
The body of the then part is the exit of the recursion returning the value 1 in register $v0.
We use shift right once for integer division by 2 and update argument register $0 before the recursive call.
After the recursive call, the result of this instance is 1 more than the result from the recursive call.
The subroutine to compute the length in binary guides the design to a recursive one that performs the filling of an array with the characters of the binary representation.
It is simpler if we place the least significant bit, found by testing division by 2, in the given position, and the later part of the binary further in the array.
When we print out the binary representation, the routine has as a parameter the position to start printing from, thus, the string of chars for the binaries in reverse order for how they're in the array.
These 3 recursive functions enable the entire program.
But since the design essentially scans an array, we can design slightly more efficient versions with pointers.
Now, the argument is the current position where the binary character is to be placed.
The code computes the character, and then calls itself recursively with half the value and the following position as the new arguments.
The pointer version of the subroutine to output the characters scans from the highest position down, decrementing the pointer.
Note that the pointer versions also have fewer parameters than the array versions, which implies slightly more efficient code.
Fewer instructions are needed to allocate space in the stack for parameters.
The assembly version of the conversion to binary, with pointers, has the structure where we need to save the return address. It is recursive, and has 2 arguments.
We place the parameters in S registers, so any further subroutines must respect them and release the argument registers for new parameters to recursive calls.
The first part requires an if-the-else control structure testing the least significant bit.
The corresponding ASCII value is stored where the pointer in register $S1 indicates.
A second if-the-else control structure tests whether a recursive call is necessary.
A recursive call is made only when the parameter in $S0, that is, the value, is greater than 1.
In this case, the preparation of the new parameters, which includes dividing the value by 2, and shifting by 1, the arrays of bytes, happens before the recursive call.
The assembly for printing the array of chars with binary representation is analogous.
The structure starts with saving in the stack the return address and 2 more S registers, because these 2 S registers will be used for the parameters.
The end restores the return address and the values of the 2 used S registers before returning the control to the caller.
The body is an if-then control structure, with a system call to print the character. Notice the load byte, and not word, pointed to by the parameter which was stored in $S0.
After that, the code prepares new values of the parameters for the recursive call.
The pointer is decremented once in $0, while the second parameter is untouched.
We now illustrate the dynamic allocation in assembly into the stack.
After reading the input and finding its length in binary in the main assembly program, we want to shift the stack pointer as many bytes as possible to fit the binary representation routed to the next word.
There is a bit of arithmetic to do this before shifting the stack pointer by the value in $S5 and then copying the value of the stack pointer in $S2.
This value in $S2 is the base of the space allocated and used as a parameter in the calls of the recursive functions.